So let's start the next chapter. In this chapter, we are going to see applications of derivatives. And this is the first section, which is about extreme values of functions, maximum and minimum values. And the first result is this one, theorem 1, which has this name, the max-min theorem for continuous functions. So let's see the statement. We have a function f here, which is continuous at every point of some closed interval I. F is a real valued function, of course. We are only working with real valued functions. And f is continuous inside a closed interval. If so, then f assumes an absolute maximum value capital M and an absolute minimum value small m inside I. Now let's see what this means. And this is the meaning, that means the statement continues. That is, there exist 2 points, 2 real numbers x1 and x2 in the interval I, such that f of x1 is that smallest value small m, f of x2 is that largest value capital M, and to further describe that they are smallest and largest respectively, we have these inequalities. Small m is less than or equal to f of x, which is less than or equal to capital M for all x belonging to I. That is the meaning. So that means this theorem is saying that if we have a function which is continuous on a closed interval, then somewhere in the closed interval, the function assumes its absolute minimum value, and somewhere in the closed interval, it assumes its absolute maximum value. And these are some typical situations. Let's consider this case. The closed interval I here is the interval a comma b, where we have the graph of some continuous function. So you can see that within this interval, this is a point x2 where the function is attaining its maximum value capital M, which is an interior point of the interval a comma b. Similarly, you have x1 here. At x1, the minimum value small m is being attained by the function. In this second one, the absolute maximum capital M is attained at the left end point. This time it's not an interior point, but it is still, of course, inside the interval because we have closed interval a comma b. So here a itself is x2, and the minimum value is also attained at the other endpoint, the right endpoint. That can happen. This is also a continuous function, the graph of a continuous function. In this next one, the absolute minimum small m is attained at the left endpoint A. However, the absolute maximum is attained at an interior point x2. In this last one, the absolute minimum m is attained at an interior point x1, but the absolute maximum is attained at the right endpoint. So all these possibilities are there. Whether the minimum or maximum is being attained at an interior point or at boundary points, that means endpoints, they will be attained somewhere. Note one more thing, that the theorem does not say anything about whether these points will be, these values will be attained at some unique points. The same maximum value may be attained at multiple points also. We will see examples of that. And you see that in this first example itself, example 1, where in this closed interval between minus pi over 2 and pi over 2, we consider the function, the cosine function, cos x, whose graph you already know looks like this. Of course, you can understand that I cannot draw the accurate graph. It just shows the shape. Okay, that's how it generally looks. So this takes on a maximum value of 1 once. This value is taken on at the input x equal to 0, and in this interval it's taken on only once. However, the same function also attains a minimum value of 0 twice, here as well as here. So that can happen. However, this other function, the sine function, takes on its maximum value 1 and minimum value minus 1, both only ones. 1 is taken on at pi over 2 and minus 1 is taken on at minus pi over 2. The max-min theorem, what does it say? It says that a function of this type assumes a maximum and a minimum value somewhere in the interval. Note the hypothesis carefully. The function should be defined, or at least should be considered throughout a closed interval. The type of the interval is important, and it should be continuous. In this means continuous at every point of this interval. If any one of these two conditions is not there, then maximum or minimum values may not exist. Now we are going to see two examples of this happening. This is one of the examples where the function is the identity function and we are considering it on the open interval 0, 1, not closed interval. We know that it's continuous in this interval at every point of this interval. So continuity is there, but the interval type is not but is given in the max-min theorem. And the function fails to have any maximum or any minimum value. You can understand why if you just look at the graph. The graph, of course, is this line, but not entirely, of course, because we are only considering the input from here. So it's this line segment without its endpoints 0, 0 and 1, 1. Can you think of a point where a maximum value is being attained? That point needs to be inside the domain. If, say, you choose a point very close to 1, say x, but because x has to come from here, x needs to be less than 1. So there is a small gap between x and 1. If you choose another input from that gap, then the corresponding output will be larger than the output f of x. So there is no absolute maximum. Similarly, there is no absolute minimum. So in spite of being continuous, the function fails to have a maximum or minimum in this interval simply because it's not of this type. So that can happen. That is why closedness of the interval is important. And the other example is this function f, this time defined on this closed interval. So now we are taking closed interval minus 1, 1 into r, of course, but the definition of f is given like this, partly. Okay, its definition is of different type in different parts of the domain. If your input is, of course, greater than or equal to minus 1, but less than 0, that means if it is negative, then f of x is defined to be x plus 1. But if your input is 0, then the output is defined to be 0. Whereas, if the input is positive and less than or equal to 1, then the output is x minus 1. And if one draws the graph, it looks like this. In this region between minus 1 and 0, not being equal to 0, the graph is this straight line, where this end point is included, but this one is not there, because that corresponds to the input x equal to 0, for which the output is 0. That does not follow this part of the definition. Similarly, in this region, the graph is this. For this part, this point is included, whereas this point is excluded. So you see that this time, in spite of having a closed interval, the function is not continuous at the point x equal to 0. Elsewhere it's continuous, but because it has failed to be continuous at a single point, this one also, just like the previous one, has no maximum value and no minimum value. As you approach 0 from the left side, you continue to get larger and larger values without any end. At 0, however, suddenly the value drops to 0. Similarly, if you approach 0 from the right side, the closer you get to 0, the smaller the value gets. So there is no largest value, there is no smallest value. So failure to be continuous at even one point has caused that conclusion. It's no longer true. So continuity is important and closedness of the interval is also important. Both should be there. Otherwise, things like this can happen. Now next we are going to distinguish between absolute and local extreme values. Absolute extreme values are also sometimes called global extreme values. Extrema is the plural of the word extremum. Extremum means either maximum or minimum. So we have a definition here. Let's see. The definition of absolute extreme values. After this definition, we have another one where we will see local extreme values. Let f be a function with domain D, which is a subset of the set of real numbers. That's understood, and f is also real value. Then f is said to have an absolute maximum value in D at the point x equal to c, which is also a point in D, if f of x is less than or equal to f of c for all x belonging to D. It's a simple thing. No, I mean, if this happens, then we say that f attains a global or absolute maximum value inside D at the point C. So this f of c is that capital M. Similarly, f has an absolute minimum in D at the point C if this time f of c is less than or equal to f of x for all x in D. So in this case, this f of c is that small m. Next, let us see in example 2 4 cases of the same function, where if we change the domain, then this situation of attaining or not attaining extreme values will change. This is the first case. The function is the real valued function defined on the entire real line, and it's your usual square function. If you draw its graph, you know that you get this parabola which opens upwards and it passes through the origin 0, 0. So from the graph or otherwise, I mean, if you want to argue analytically, that also you can do. You can clearly see that there is an absolute minimum value of 0 at the input x equal to 0, but there is no absolute maximum. The further you go away from the origin, the higher the values get, either on this side or on that side. So what about the theorem, max-min theorem? Well, that theorem in this case is not applicable, because although the function is continuous, but this is not a closed interval. So there is no guarantee for having extreme values. Still we have an absolute minimum value, but no absolute maximum value. Now if we change the domain to this half open interval, open 0, closed 2, then the situation changes. Now the graph is this, which is the part of that parabola. Which part? The part that lies between these 2 points, 0, 0 and 2, 4, where 0, 0 is no longer a part of the graph, but 2, 4 is. So you can see that everything has changed. For this function, there is an absolute maximum at the point 2. 2 is a point in the domain because closed on this side, and the maximum value is 4. However, there is no absolute minimum. That 0 is no longer present. Now if we change the situation slightly by removing 2 from that previous domain and consider this open interval 0, 2, then that maximum value is gone. Now in this case, there is no maximum and no minimum. So it's like that example where we have the identity function considered in the open interval 0, 1. This one is also continuous, that one is also continuous at every point of those domains, of their respective domains, but they fail to have extreme values, absolute extreme values, because the domains are not closed intervals, and so the max-min theorem is not applicable. If, however, we do consider the closed interval 0, 2, then max-min theorem is applicable, and now we must get a maximum value and a minimum value somewhere. And looking at the graph, you see that the maximum value is attained at 2 and the minimum value is attained at 0. The maximum being 4 and the minimum value being 0. And next we see the definition of local extreme values. Again, let f be a function with some domain D, and this time let C in D be an interior point of D. Then we say that f has a local maximum value at the point x equal to C if there exists an interval I. The type of this interval is not important, it may be open, closed, anything, but these are the conditions. I needs to have the point C inside of it, and I needs to be a subset of D. That means it should be inside D, contained in D as a subset, and f of x should be less than or equal to f of C for all x belonging to I. So a local maximum is like a local champion in something as opposed to a global champion. D is the entire world. Say you are thinking of strongman championship. Okay. D is the entire world. The strongest man is the global maximum. Whereas a local champion in strongman championship, there are local games where people win prizes. So those people are like local maxima. Okay, so that's how you can make sense of it. Within this small region I, f of C is the maximum, but you may have larger values of the function outside of this region. If such a region exists in which this happens, then we say that f attains a local maximum at that point C. And we can modify this definition for local minimum as well. F has a local minimum value at x equal to C. Again, same setup. C is an interior point of D if there exists again an interval I such that C is in I is inside D, and this time f of C is less than or equal to f of x for all x belonging to I. Next, let us consider this. It's the graph of a continuous function in the closed interval with n points A and B. Let's see what the extreme values are. At the left endpoint A, you have the absolute minimum value, which is the smallest among all possible f values. At this interior point C, you have a local maximum value. Note that it's not the largest lies here, but in a small region containing C, it's the largest. It is that I that we are talking about here, not this one but the previous one. Similarly, at D you have a local minimum value. This is not the smallest value, there are smaller values on this side, but in a small interval containing D, this is the minimum because the other values around it are larger. At the interior point E, you have this absolute maximum value, which actually is also a local maximum. Being a champion in something all over the world also automatically makes you a champion in a local region. In that sense, this absolute maximum value is also a local maximum. What about the point B? Well, actually a local minimum value is being attained at B. However, to be able to say so, we need to extend this definition to include boundary points, that is endpoints. You just have to simply write that x equal to C is an endpoint. That's it. The value at B is quite large, larger than many other values, but in a small region containing B, it's the smallest because the other values are even larger. Okay, so in that sense, the value at B is a local minimum. And Now I am coming to that, the distinction between this one and this one. What type of distinction? You see one thing here, the graph is smooth here at this point, whereas there is a sharp corner here, which just means that the graph is differentiable at, the function is differentiable at C, whereas the function is not differentiable at E. Having a sharp corner means the function is not differentiable because there is no unique tangent. Here we have a unique tangent. Here also we have a unique tangent. Here we do not have unique tangent. And the thing to be noted here is that these tangents are horizontal, which you can understand should happen if you have a peak like this or a valley like this. Or in other words, if the function is differentiable at a point where either you have a local maximum or a local minimum, then the tangent at that point should be horizontal, or the value of the derivative should be 0, because that is the slope of the tangent. And this gives us a result for recognizing points in an interval where a function can possibly have local extreme values. And that result is this, theorem 2, which has this name also, the first derivative test for local extreme values. Suppose you have a function f which has a local extreme value, that means a local maximum or a local minimum value at an interior point C of its domain, where additionally f is also differentiable. That means f prime exists at C. Then the derivative value at C has to be equal to 0, which means that the slope of the tangent at that point to the graph of the function needs to be horizontal. And this will help us immensely to locate those points where the function possibly has extreme values, local extreme values. In the next calculus video, we are going to prove this theorem, and then we will see what other things we can say using derivatives.